Afternoon, friends. It's Ben again with another spectacular video for the vector calculus class. And I'm wearing my pink shirt. So um, anyway, the thing we're going to talk about today is linear first order equations. In a sense, the thing that we do with them is connected to something for higher order linear equations. It's referred to as the variation of parameters. If we have time to get to that during the semester, I'll show you what the connection is. But the essential notion is that you have to have a first order equation, so no second derivatives, and it has to be linear. That means that you can't have you can't have a square or a sine or anything acting on either the dependent variable, the y, or its derivative. Neither can you have them be multiplied together. So there's some things that you could solve as separable equations that you cannot solve with these linear first order. But likewise, there's some things that you can solve with this that are they're not separable equations. So we're getting some new stuff. Let's take a look at the statement that I've got here, because this is one of those where it's a lot easier to show it than it is to say it. Yay. Okay. So linear first order equations, they may not be given in this form, but you have to be able to put them into this form. So if there is a coefficient here for your y prime, you need to divide it out. Once you've got that, then we're going to take that p and we're going to integrate it and exponentiate it. Should seem pretty random, right? But here's the thing. If you have an exponential and you take its derivative, you get back the same thing, but then times the derivative out there. So you'd get this times the p of t out there. So this thing that we refer to as an integrating factor, when you multiply it through, will make the first part into mu y prime from the product rule. That means that when you integrate this left-hand side, it's super easy. You just drop the derivative. The right-hand side may not be so easy, but it's something that's hopefully you can integrate. And then you'll take and just divide out that integrating factor. Now, oftentimes, the thing that you've got in here is that integrating factor turns out to be something so that it appears again after you integrate, like, an e to the t or something. And so you'll get to cancel it out, but it's not guaranteed. Some things that you could have in here are not going to appear directly in the result from the integral, and thus that mu does not cancel out. It doesn't travel through the integral. So easier shown than said, I think. So we're going to look for a solution here. And after we look for the solution, we're going to try to find out about the behavior. What do I always do? I always go to Desmos to get a graph of it. So let's see what we can do. Right, first thing, that 2 over t, notice we've already got it into the form we need it. That 2 over t, we're going to have to integrate it. Integral, I wanted to use thinner lines, 2 over t dt equals 2 ln t plus c. Now, here's where I'm going to give you a bad habit. Don't worry about the plus c. That's not really important to us, okay? What is really important is that if you pull that inside, now you have a t squared, so that our mu being e to the log t squared, and don't worry about the c, is going to be just t squared. So when you take this equation and multiply through by t squared, you would have t squared y prime plus 2, the t you're dividing by will cancel one of those, y, and then is equal to the cosine of t. So this left-hand side is really t squared y quantity prime. When you did the product rule there, if you were going to go ahead and work it out, you would have a t squared y prime and a 2ty because they take turns. Now integrating on both sides, we'll get a t squared y, and the integral of cosine is sine t. Here we do have to pay attention to the c, okay? And so now trying to solve explicitly for our y, we'll get the sine t over t squared plus c over t squared. And now we're going to go ahead and plug in the the pi for t and the 0 for y. So 0 equals sine of pi is 0 and plus c over pi squared. Well, gosh, it turns out that the c on this is going to turn out to be 0. So we ended up with y equals sine t divided by t squared. All right, did I leave my Desmos running? I did not. Yeah, okay. So let's get it opened up here. And we said that that was going to be sine t, but Desmos likes me to use x's divided by x squared. Okay, so if I go ahead and look at just the graph here, you can see that on the on the x-axis or the y-axis there, we're getting something going off to infinity. But what we were actually asked to look at is to describe what happens as t goes to infinity. So I'm going to take and smoosh my t-axis in here, and then I'm going to expand my y-axis so I can see a little bit better. So I've said this to some of y'all before. I like the Desmos app on the iPad better than I like it on the web, because I can grab it and manipulate one axis at a time just a little bit easier. There may be a way to do that on the website one, but that should show us what we need there. We have a solution which, as t goes to infinity, is going to 0. So we've got a a horizontal asymptote. So down here, I'm going to say, as t goes to infinity, y goes to 0, right? That sort of thing is often referred to as asymptotic behavior. And that probably seems kind of trivial to say to y'all because it was defining a horizontal asymptote for us. But there are other kinds of asymptotic behavior. You can say things are going to infinity or they're oscillating, things like that. So, all right, let's take a look at another one here. And for this one, we're asked, find all the solutions to this guy here. And we've got this condition, but they kind of cheated on the initial condition. They didn't give us an actual number. So we're going to have to just deal with that number, or deal with that as being A, and just see what we do with it, okay? So first thing that you'll see is that we've got a t for the coefficient of y prime, and we don't like that. So I'm going to go ahead and divide through, and that should look familiar. But it gives me that. So now my mu is e to the integral 2 over t dt, which is going to be e to the log of t squared, which is going to be just t squared. So I'm going to multiply everything through by t squared, and I'm going to just collect the stuff on the left-hand side as I go and say that's equal to sine t, right? Because the t squareds are canceled. Now when I do my integral, I'll have t squared y equals, let's see, minus cosine t plus c. And then this might be the place where it would be most convenient to actually get my a involved, right? Because if I go ahead and plug that in, the t squared that appears there, we'll have the minus pi over 2 for that, and times the y value of a is equal to the cosine of minus pi over 2 is 0, and then we'll say the plus c. So that says that my c value that I need to involve in here is going to be equal to a pi squared divided by 4. Okay. I have the urge to be funny there. If you get a square pi, that's called a cobbler here in the South. Please don't shoot me. I know that was terrible. But now, if we solve for a y on this, we'll end up with a minus cosine t divided by the t squared, and then plus the a pi squared over 4 t squared there, okay? And so we're going to describe the behavior and see what happens here. And it should be fairly easy to do that. So normally I would ask y'all to remember that, or I would be on a marker board or something where I could see it as I went along. But but I am going to have to jump over here to Desmos. I'll bring this out, we'll kill that, and we're going to put in there, it was cosine t, or minus cosine t. So here's my minus cosine, except I can't say t, it's got to be x, parentheses. Oh man, look at what that did. Okay, so I've got to adjust my axes. There we go. Okay, that's a little better. But then we are dividing by what? X squared. And then it was plus a, and then we're going to add a slider. And the a then had a pi squared. And so pi squared. And then we had to divide it by 4. Okay. So now, if I hide that, my slider goes away. All right. So you can see that the main big thing that's happening there is at, sorry guys, I'm supposed to have that in there. Okay. Now I am going to go ahead and add something in here. The thing I'm going to add is the initial condition. It was minus pi divided by 2, and then comma, and then the a. And then I want parentheses, and I want a label on that. Okay. All right, that way we can see what's going on there a little bit better. And sorry, I can't hide more of the controls on this. So we've got something going off to infinity there. And you can see that as the x is going to infinity, that we're getting something going to 0. But what I really want to show y'all has to do with the slider here. And I'm going to just tell it to go from minus 5 to 5, so I have a little bit more control about it. So, you know, as you push the a in the positive direction, you can see that it's doing that. And as you push it down here, there's a certain point at which it just suddenly flops around the other direction, right? So it's maybe not too weird to think that some A values are going to make you have a negative direction there, and some have positive. But look carefully at what's happening. It's not happening at 0, right? So zoom in on that spot a little bit more. And I'm going to change this and go from -1 to 2. And that way we can kind of see that it's coming down here, and right around 0.41 is where it has that change at. That's kind of wacky, isn't it? So you might, hopefully, you might be curious as to why that's doing that. And the key thing to it is if we go ahead and mess with our function here so that we get least common denominators, see how now you would have, and I didn't change it, I just put the least common denominators in there. Now you would have 4 cosine x and the a pi squared. And the thing that's happening here is if you went ahead and expanded out your cosine as a Taylor series and looked at the constant term there, you would have a 4. And when the a makes the a pi squared be equal to 4, that's exactly when that change is happening. So the answer to the question here is, where does it change? So change around a equals 0.41-ish when a pi squared equals 4 and due to Taylor expansion. Okay, so the thing that's happening is that you're just losing your constant term there exactly when the a hits that value. That's kind of interesting. Okay, a lot of the differential equation stuff, we're interested in what happens when we change various values on the functions here. So, all right, so same sort of thing with this problem. It's asking us to solve another linear differential equation. I have again purposely put one as the t times y prime, so we have to do a little bit there. So with doing that, you will turn it into y minus 1 over t, oops, that's y prime minus 1 over ty is equal to t e to the minus t, okay? And so then the thing that you have to look at here is we'll have e to the integral minus 1 over t dt. So that's e to the minus log t, which is going to end up being 1 over t. Okay, I skipped a little bit there. So if you multiply 1 over t through there, then you end up with this e to the minus t. Okay, and gosh, I thought I had something up. Bear with me here. I might have to modify this a little bit. So what we've got here is 1 over t y prime equals e to the minus t. And we integrate both sides, and 1 over ty is equal to minus e to the minus t plus c. Then when you multiply both sides by the t, you end up with y equals minus t, e to the minus t. Oh, that's what's happening. Okay, plus ct. All right. So do we have an initial condition? We don't. Okay. So let's go back here to Desmos, and I will have to, off to the side, write out my function that we're going to look at. And so we're going to, this time, have minus x e to the, so it's under miscellaneous, goodness, exponential of minus x, close parentheses, and then plus cx. So I'm going to say plus a, because I already get the slider there, x. Okay. So we're going to take a look at what's happening with this. And it's kind of an interesting thing there. Notice it always is going through 0, 0, right? But that as we pass through that 0 part, I think that question was sort of incidental to what's happening here. What you're going to run into on a couple of the questions that I've gotten for you on the homework is asking you to keep an eye on what happens and try to solve here for what the first maximum and minimum was for it. If it turns out that there's more than one. There's also something that happens right here. If you'll notice that a being your slope of a line, what we've actually got occurring with this one is that your asymptotic behavior is going towards a straight line. So when the c equals 0 in particular, the a, I guess, equals 0 here, the asymptotic behavior you have is going to be the x-axis, right? But a more complete answer then here, might be to go ahead and say that the solutions tend towards the line y equals ct. Okay, and the reason really behind that is because right here, as t goes to infinity, that portion is going to go to 0. Okay. So to answer the literal question that was asked, so as c equals 0, the solutions tend to vanish at infinity. There's a technical math term. We like to use anything that's going to 0, we say vanishes. And if it's happening asymptotically, we may also say that it's happening at infinity, or as we tend to infinity. So I thought I had another example here that did something neat. I guess not. Okay, I must have cut that out for time. All right, so that got you a few little examples here. It's not really a lot, but it gets you going about how we're getting the solutions. Then the other questions that I'll ask you to do are really explorations that you can do by looking at Desmos or something else. Please bear in mind, if the integration gets just too gnarly, you can always turn to Symbolab to do that, but don't turn to Symbolab as your very first choice, because if you don't know how to integrate anything, the exams suddenly get very challenging. So, all right, that should do it. I'll see you in class.